So we will look at some important LTI systems, and the first one we will look at is an all-pass system. An all-pass system allows all frequency sinusoids or all frequencies to pass through it because it has a frequency response which is a constant, that is the magnitude of the frequency response is constant for all frequencies, and that's why all frequencies are able to pass through this all pass system. So to be able to understand this all pass system more, let's look at the system function of a simple all pass system, and this is the system function: Z inverse minus A star divided by 1 minus AZ inverse. So we will notice that in this all pass system, from its system function we observe that it has a pole at, over here we can see that there is a pole at Z is equal to A, and it has a 0 at 1 over A conjugate. The 0 is at 1 over A conjugate, because if we put a 1 over A star 1 over A conjugate here, uh, over here instead of Z inverse, so Z inverse will become A star. So A star minus A star is 0, so we can see that there is a 0 at 1 over A conjugate. So this is the form that all pass systems have. There is a 0 at, if there is a pole at A, there will be a 0 at 1 over A star, and this is called a conjugate reciprocal position. And we can see this from here also. If A is any complex number R, E, J, theta, for example, if A is, the pole is located at 0.8 EJ pi by 4. So over here we can see that we in this system there is a single pole at 0.8 radius and the angle is pi by 4. So here we have a pole in this system. A is 0.8 EJ pi by 4. So the 0 is at the conjugate reciprocal position, which is 1 over 0.8 EJ pi by 4. So 1 over 0.8 is 1.25, so it's outside the unit circle over here, and this is where the pole is, but the angle is the same, it is at pi by 4. And we can see why the angle is the same, because if A is REJ theta, then 1 over A star is 1 over REJ theta conjugate, right? Conjugate of REJ theta is RE minus J theta. Because this term E minus J theta is in the denominator, then it becomes REJ theta in the numerator, and so the 0 or the conjugate reciprocal position is 1 over R EJ theta. So the 0 is at 1 over 0.8 EJ pi by 4 or 1.25, and angle is EJ pi by 4. So we can see that these are this system function, which is the simplest all pass system. It has a single pole and a 0 at conjugate reciprocal positions. Let's find the frequency response of an all-pass system. The system function was given as we saw in the last slide, HAPZ is equal to Z inverse minus A star over 1 minus AZ inverse. And we can obtain a frequency response from system function by replacing Z is equal to EJ omega. So over here in the system function, we just replace Z by EJ omega. So Z inverse becomes E minus J omega minus A star, and we have 1 minus AE minus J omega in the denominator. Then we could simplify this. We take out this E minus J omega term. We take that out. We take E minus J omega from the bracket, and then we have our all pass EJ omega expression in this form. Now, if we want to find the magnitude response, how do we do that? We just want to find the magnitude response, which is we so what we'll do is we'll just take H A P E J omega. Magnitude will be the magnitude product of magnitude of all these terms. So the product of magnitude of all these terms is, we write it over here like this. So let's find out the magnitude of each of these terms. So magnitude of E minus j omega will be 1, because this is a complex number which has a magnitude only of 1. So E minus j omega is 1. And these two terms, when we look at them, they are actually complex conjugates of each other. 1 minus a star e j omega and 1 minus a e minus j omega. They are complex numbers, and they are conjugates of each other. So, a complex conjugate numbers, they have the same magnitude, right? For example, if we had a number a plus jb, then the complex number a minus jb has the same magnitude. So these two terms in the numerator and denominator, they have same magnitudes, so they will cancel out, and as a result, we have the expression for magnitude of the all pass system is 1. HAP omega is 1. So that means that all pass system has a constant magnitude response of 1, which means it allows to all frequency sinusoids to pass through the system with a constant gain of 1. They are allowed to pass as it is. So it does not attenuate the signals at all. But however, it may add a phase shift, but the magnitude response is 1. We saw that the magnitude response of an all-pass system was a constant 1 for all frequencies, and it allowed all frequencies to pass as it is, but there is a phase shift added, and the expression for phase shift is given as over here, minus omega minus 2 arctan, right, r sine omega minus theta 1 minus r cos omega minus theta. So this is the phase for a system which had a pole, right? Our system had a pole at um, rej theta and a 0 at the reciprocal location. So right, we can compute the phase for that also from this expression for this all pass system. So because all pass systems can introduce a phase, but they don't change the magnitude of an input signal. So if what we want to do is that we want to just compensate for a certain phase which is being introduced or delay being introduced, then we can pass the system a signal which has undergone some phase distortion. We pass it through an LTI system, and the LTI this all pass system, and the all pass system won't change the magnitude of the signal, but it will just introduce a delay or a phase shift, and in this way we can use all pass systems to compensate for phase distortion. We saw the system function for an all pass system which had a single pole at A and a 0 at 1 over A star, conjugate location, reciprocal location. But this system is a first order system. This simple system is a first order system, and the degree of Z inverse is 1. So it's a first order all pass system, and we can combine uh, many more terms of this form, as many as we like, and we can form a mth order general all pass system. Right? We could combine more terms. We can add more zeros and poles at conjugate reciprocal locations, and we can form an all-pass system with a higher order. Right? So if we have three terms like this, then we will have a all-pass system of order 3. But each of these poles and zeros in each of these terms will be, each of these simpler factors will be consisting of a pole at A, and it will be paired with a 0 at the conjugate reciprocal location 1 over A star. And even though we are combining, right, more of these terms, m of these terms, so each first order term has a gain of 1. So the overall gain will still be 1, because when we combine system functions, we know that when we combine LTI systems in cascade, their gains, in their system functions h of z are multiplied. So overall gain is still 1. And right, we'll look at some examples of all pass systems, right, of different orders. So we'll consider an example of a all pass system, which is the second order system, and it has two poles. Right? One is at zero point 0.9 ej pi by 4, and the other one is at zero point 0.9 e minus j pi by 4. So let's consider the first pole located at zero point 0.9 ej pi by 4. So it's this one, right? So the unit circle is at radius 1 and the pole is at zero point 0.9 but at an angle pi by 4. Now the 0 corresponding to this pole is at a conjugate reciprocal location, which is 1 over zero point 0.9. So the 0 is at 1.11 and angle ej pi by 4. So this is the 0. It is at 1.11 ej pi by 4, and that is at an angle pi by 4. So this is the first pair of the pole and its associated 0 at the conjugate reciprocal position, and the second 0, the one at uh, minus pi by 4 angle, right? So this is the pole at zero point 0.9 angle pi by 4, and its associated 0 is at right 1.11 or 1 over zero point 0.9 radius, uh, located at this radius, but the angle is also minus pi by 4. So the pole and its associated 0, when we look at them, they are at mirror po- positions as respect to the unit circle. We can think of them as being reflected about the unit circle. So the pole is at the same distance from the unit circle as the 0 is. If we measure this distance and this distance. So the mirror reflections about the unit circle. This one also. Right? This is the pole and its 0 associated 0 is reflected about the unit circle. If you look like this. Right? So this was the pole 0 plot of our second order all pass system, and then we will look at what type of a frequency response does this all pass system have, this second order all pass system have. So we can look at the frequency response plots for the second order system that we just saw now. So we have the log magnitude plot. So we see here that the system has a constant gain of 0 decibels or magnitude 1, HEJ omega is 1. So log magnitude is 0 dB. So it has a flat uh, frequency response magnitude part. It allows all frequencies to pass as expected. And when we look at the phase part, we see that phase is falling up till this frequency pi by 4, and then it certainly has an abrupt change and rises, and then again it goes like this, and another abrupt change at this frequency, which is 7 pi by 4, right? And this is because the system had a pole 0 pair located at pi by 4, we recall, and there was another pole 0 pair at point 9 e minus j pi by 4. So, right, and e minus pi by 4 is the same as 2 pi minus pi by 4 or 7 pi by 4. So the phase changes at the location of the pole 0 pairs, one over here and one at this angle, right, equivalent to minus pi by 4 um, angle. And if we look at the group delay plot, so group delay, as we know, is the derivative of the phase. So if we take the derivative of this phase function, we would get the group delay. And here the phase rises as sharply, and so there is in the group delay plot we see a sharp rise over here also, and here it phase rises abruptly, so its derivative will also rise, will have a high value, and so this is our group delay plot for the second order system of our example. And here the group delay is about 18 samples. So this system mm, will have a flat magnitude response plot, but it will introduce some phase shift, and it will also delay its inputs, sinusoids, and the amount is that at pi by 4 the sinusoid um, will experience a delay of 18 samples. So it could be maybe useful if we want to compensate that signal has already undergone some delay and we want to maybe compensate that delay, then we could use a system of this form.